Hello, welcome to CSC7013, Advanced Math for Computer Scientists. This is Brady Chen. Today, we can talk about Boolean Algebra and its application in digital electronics. That's the second part, and this is Module 3. So in previous module, we discussed the relationship between logic circuits and the Boolean expressions. Now we're talking about how to create a logic circuit or circuit diagram based on the Boolean expression, or vice versa. As we know that there are an infinite number of Boolean expressions that are logically equivalent to one another. Now, that is to say that there are also an infinite number of corresponding logic circuits that can perform the same functionality. Now, the question is, how can we tell that a circuit is in its simplest form? Because you can have so many different circuits, and which circuit is the best one? And here's learning objectives for Module 3. We'll first continue to talk about how to simplify a logic circuit. Okay. So we briefly talk about the relationship between logic circuits and a Boolean expression. So we know for each circuit we can, create corresponding logic expressions, and then we can simplify the logic expression, and then we can recreate a new logic circuit that is equivalent to the original one. Now, then the second part, we're going to talk about a circuit device called the Reset Flipflop. A flip-flop is a very simple storage device that can store just one bit, and we're going to talk about this. And then we're going to provide more examples. So as we mentioned earlier, that there are an infinite number of Boolean expressions that are logically equivalent to one another. So that is to say that there are also an infinite number of corresponding logic circuits that can perform the same functionality. Now, the question is, how can we tell, or how can we choose a circuit that is in its simplest form? Now, to answer the question, let us assume that there are two logically equivalent circuits. There are two logically equivalent circuits. One requires more digital logical gates, than the other one. Now, so we can rationally assume that the circuit with a fewer number of components should increase the reliability, because it actually consists of fewer number of gates, fewer number of components. And this should increase the reliability, decrease the manufacturing cost, and consume less electrical power. So thus this is going to reduce the operational cost. So if you have two circuits, one has fewer components, and we believe that circuit is the one which is better than the other one. Now, the question now is how to simplify a logic circuit. Now, so suppose I have a logic circuit, okay, which has a design, so which contains some of the AND gate, OR gate, something like this, okay. So we have OR gate, something like this. Okay, so that's the logical circuit. Now, how can we simplify this? So here are the steps. Now, the first thing we need to do is we need to translate a logic circuit into the corresponding Boolean expression. So let's say, based on this, we can convert into some kind of Boolean expression, like f of x, y, z. Suppose we have, x, y, z, a, x, y, z, a. Okay, so there are 4 imports. Okay, so if there are 4 imports x, y, z, a, and then so we try to actually convert this into a Boolean expression, something like x times delta y or plus blah blah blah. So now the next step we're going to do is simplify this Boolean expression. So somehow, if we can simplify this Boolean expression, so then we know once we done this part, the new Boolean expression going to be equivalent to the older one. So they are equivalent, and hopefully it will be simpler, which contains fewer number of operations. So how can we simplify this? We can simplify the Boolean expression with algebraic rule, like all these, algebraic identities. So, and then we regenerate the circuit diagram with the new expression. So we generate the circuit diagrams from the simplified expression with fewer gates or components. So we start from the logic circuit which contains many components, and then we convert into a Boolean expression, and we simplify the Boolean expression which contains fewer number of operations. Okay, and then we generate the circuit diagrams from the simplified expression. Now we actually complete the simplification of a logic circuit. Now, to this end, there are several rules of a Boolean algebra presented in the previous module to reduce the expression to the simplest form. Okay, so the Boolean identities we discussed earlier, which contains several, identities, like identity law and, associative law or commutative law. So there are so many these Boolean identities. Okay, so we can use this identity discussed in the previous module to perform this simplification. So now let's take a look at the following circuit we discussed in the previous module. I think it's the last slide in the previous module, and figure out how to simplify it with the Boolean laws we discussed in module 2. So the first thing we need to do is we need to identify all the gates. Okay, now there are 3 AND gates. There are 3 AND gates. Here's the one, the other one, the other AND gate, and another AND gate. And there are 2 OR gates. Okay. Now we have 3 imports, A, B, and C. Now the first thing we need to do is, based on the input, we need to figure out what is the output of these 3 gates. Now first let's take a look at the the AND gates on the top. So for this AND gate, there are two inputs. One is actually A, the other one is B. So what is the output? It's A times B. So it's A and B. And then let's look at the OR gate in the middle. So what is the input? The input is B here, and also the bottom. At the bottom, the input is C. So now we have a B plus C. And the last one, the bottom one, which is the AND gate. So we have input C and also input B. So we have C times B. So here's the result after first round. So now we're going to actually look at the output for the next two gates. So first look at the AND gate over here. So the inputs for this AND gate are B plus C and B times C. So then the output should be B plus C times B times C. Okay, so that's what we got. So here's what we have after second round. So now let's take a look at the last gate, which is the OR gate. Okay, after the last gate, we will get the final result. So that's the OR gate. So there are two inputs, A times B and this expression. So we have A times B plus the other expression, B times C times B plus C. So this is actually the final result. So that's the Boolean expression corresponding to the logic circuit we have here. So that's the final expression. So we have the final expression Q equals A times B plus B times C times parenthesis B plus C. So that's the final expression. Now the next step we can do is, can we simplify these logic expression, the Boolean expression? We will see. Okay, that's a step 2 of the simplification of a circuit. So we're going to apply the rules of Boolean laws, or the Boolean identities we discussed in Module 2. Okay, so let's say the Boolean expression corresponding to the circuit is this. Here's the Boolean expression. Okay, now the first step we can do is we try to expand all these terms, the second terms, now B times C times B plus C. So we actually take a look at the second term, and then we expand it using the distributive law discussed in the Boolean identities in Module 2. So the distributive law says we can actually, put this one and then multiply B and B times C with the first item. So it's B times C times B. And then we apply B times C with the second item C. So it's a B times C times C. Okay, so that's a distributive law. Now, I also put the count the number of gates in each of the expression, because each operator, like in this case, that's the AND operator, that's OR operator. Each operator, you will see that it is eventually, each operator is eventually corresponding to a gate. So let's count the number of operators here. 1, 2, 3, 4, 5, 6, 7. So we have 7 operators. We have 5 AND gates, and 2 OR gates. So we have a total of 7. Now, so the next thing we're going to do is we try to look at these, Boolean identities, try to simplify even further. Okay, so we actually switched the order of C and B. Switch the order between C and B. So we actually put the B before C. Okay. Now why we want to do this? We'll see. So why we can switch the order? Because when we switch the order, then you will still get the same result. So C times B is the same as B times C. That's based on the commutative law. So then X times Y equals Y times X. Now this doesn't change the number of gates. Okay. And then the next one, you have a B times B. So we can take a look at this B times B. We find out, well, we can simplify this part because B times B is the same as B. So that's idempotent law, which says X times X equals X. So now we have a B times B. So we can reduce the number of B. And in the meantime, because we have a C times C here, so we can use the idempotent law as well for the C. So we can reduce the number of C. Okay, so now we got this Boolean expression. Now let's count how many gates here, how many operators here. So we have a AND gate, OR gate, another AND gate, OR gate, another AND gate. So we have 3 AND gates and 2 OR gates. So we have a total of 5 gates. So now let's take a look at these again. The second term, B times C, and the third term, B times C. So these B times C and these B times C, they are the same. So I can apply the other version of idempotent law, which says X plus X equals X. So now here X is B times C. And so we have B times C plus B times C. So we can actually reduce the number of B times C from 2 to 1. Okay, so that's the other version of idempotent. So the first top one is called AND form. The other one is OR form. Okay. So looks like we basically simplify these, the Boolean expression. Now we can actually do it further. Okay. So we use the commutative law again to switch the order between A and B, right? So now we can have a B times A, which is the same as A times B, and plus B times C. Okay, that's use the commutative law again. So why we want to do this? Because now we see that there's a common factor in both terms. First the B times A, the second B times C, then you can use the distributive law and you can take the B out. So now we have a B times parenthesis A plus C. Now we can actually keep the logic expression like this, but I want to do it further. Why? Can you tell me the reason why? Because that way I can reduce the number of the gates even further. Now there are two operators. Okay, one is or, the AND, the other one is OR. So this has two. Now this we still have three operators, logical operators. We have a two AND operators and a one OR operators. So we have three. Okay. So that's basically the simplest form, we believe. So now, once we get the simplest form, then we need to actually draw the circuit diagrams of the simplified form. Okay, that's step 3. Okay, now we actually proved that in step 2, we actually proved that the logic expression, the Boolean expression of the original circuit is equivalent to the Boolean expression of the simplified form, because we follow these Boolean identities, and we actually finally get that result. Now, how can we actually draw these circuit diagrams? Now, the first thing we need to do is we need to actually start from the the expression inside the parenthesis. So that's the first thing we need to calculate, right? So first we need to build the logic, circuit diagrams for A plus C. Okay, so this is what we have. So we have input A and input C. Okay, and then we have A plus C. That's OR gate. So then we got A plus C. Okay, so that's the first step. Now continue with the step 3. The next, we're going to build an AND gate. And this AND gate has two inputs. One is A plus C, right? One is A plus C. Now the other one is B. So we can actually basically combine the logic expression, the circuit diagram we just draw in the previous slide into this new diagram. So we have A plus C, okay, which is actually the output for this OR gate. And then we have another input B, okay. So then pass through the AND gate, then we actually create B times the parenthesis A plus C. So we combine these AND gate with the OR gate we just created in the previous slide, and that's the circuit diagram of the simplified logic expression. Now take a look at this diagram with the original one. We find out, so we actually dramatically simplify these circuit design, because the original diagram contains 5 gates, but now we actually reduced the 5 gates into 2 gates, and these two are identical, so that means you can actually perform the same logic operation. So let me summarize what we have done. So originally we want to simplify a logic circuit which contains 5 gates, and then we convert the logic circuit into the logic expression, which is this. And then we simplify these logic expression or Boolean expression to an equivalent one, which is much simpler. So then we just draw the circuit diagram for the simplified logic expression. Now, as we mentioned that this new simplified logic circuit only requires two gates. One is AND gate, the other one is OR gate instead of 5. Now, what's the advantage? Okay, so this is going to decrease the manufacturing cost because when we build the circuit, which contains fewer number of gates, so definitely we can make it smaller, and also it's going to increase the operating speed because we have less delay. We have less delay time from input signal transition to the output signal transition, because the original circuit, once we have an input, we're going to pass through a couple of gates. But in this time, the longest path is we only need to pass 2 gates. Okay. Now, also, because we have fewer number of gates, so this definitely going to reduce the power consumption and also improve the reliability. So this is really good. So now again, it's your turn. So I'm going to post this, logic circuit on the discussion board, for module 3. So you can actually provide your input and try to figure out what is the simplified logic expression and what's the simplified the logic circuit. So let's actually work on this. So let's talk about a special electronic circuit. It's called a flip-flop, and often referred to as a latch. A flip-flop has 2 stable states, and thereby we can use the flip-flop to serve as storage for a bit. So you can store either 0 or 1. Now, a typical flip-flop is usually controlled by 1 or 2 control signals, and the output, and normally we have 2 outputs, and these 2 outputs often include the complement as well as the normal one. So if one output gave you the output value 1, the other one gave you 0, or vice versa. There may be many different flip-flop designs. Now, the following circuit basically presents a flip-flop known as set-reset flip-flop. So the diagram shown in this slide is called a set-reset flip-flop, or sometimes we call it SR flip-flop. So this flip-flop is constructed using a pair of OR gates and a pair of NOT gates. So we basically use 4 gates. As we can see from the diagram, a SR flip-flop can be considered as a basic 1-bit memory device that has 2 imports. One import is called a set input. Sometimes we just use S. Now the other import is called a reset input. And there's an output, and the Q is the output. And the other one is tilde Q, it's a complement of Q. So the input S basically will set the device, and the input R will reset the device back to its original state. Now let's take a look at how SR flip-flop works. Now let's assume that a flip-flop is in storage mode, which means that both the set import and the reset import are set to be 0. So now the value Q is the stored data. Now Q could be 1 or Q could be 0. We don't know, and I don't care. And now let's just do this. Okay, so the set import is 0, reset is 0. Now what about if I change the value of set import to 1? What do you think? So that means one of the input of this OR gate is 1. So basically, so that means the output should be 1, right? Because it doesn't matter what is the value of the other input, because one of the input is 1, so the output should be 1. Now this is actually the NOT gate, so the output of this NOT gate should be 0, and this 0 is connected to here, which is the import of the other OR gate, so that's 0. Now since the current reset import is 0, so now both imports are 0 for the OR gate at the bottom. So the output should be 0, and then because that's under the NOT gate, so the output should be 1. Okay, so when we change the set import to 1, then this is going to change the, okay, I'm not going to say change, because this is going to set the output Q to 1, and it doesn't matter what is the previous value. Okay. Now, once we're done this, so now what about if after I change the value of set to 1 and I change back to 0? Okay, if I change back to 0, what happens? Well, let's take a look. So this import is 0. Now what's the other import now? Now the other import is connected to the output Q, right? Now the output Q is 1, so here's 1. So that means the output for this OR gate is still 1, and this is still 0, and this is still 0, and nothing changes. So Q is still 1. So that means once you actually set the import value to 1, and then you actually set the output Q to 1, and then when we actually change the set value S value to back to 0, and whatever the value stored in Q stays the same. So that's now we're in the stable state. So now both the set and the reset value are 0. So the value we stored in the flip-flop is 1, because this is a stable value. Okay, let's summarize whatever we talked about in the previous slide. Now initially, the flip-flop is in storage mode, which means both the set and the reset imports are set to 0. Now, in order to change the storage value, so we actually change the set value to 1. Okay, so then this is going to actually force the up OR gate, the output of the up OR gate to 1. remember the truth table for OR gate. So if one of the input is 1, now it really doesn't matter what is the other input, right? The output should be 1. Okay, let's move forward. So once we, set the set input value to 1, we know the output of the up OR gate becomes 1. And then the output of the up NOT gate will be 0, right? Because it's a NOT gate. So this becomes 0, and then if make the input of the lower OR gate 0. And now you have a 0 and a 0, so the output of the lower OR gate is 0. So we know once we set the upper input S to 1, this eventually changed the value output Q to be 1. Okay. Now, after this, now we need to set the set input value from 1 back to 0. So we need to set these upper input S back to 0. This will actually switch the flip-flop into the storage mode. That means the value 1 will be stabilized. So you're going to stay as a 1. So now it's your turn. Now let's assume the value Q stored in SR flip-flop is 1. And the initial state for the SR flip-flop is as following, which means both the set and the reset imports have value 0. Now, how can we change the stored value Q from 1 to 0? Now, this also applies another case. Now, if the current value Q is 0, and so how can we set, just refresh the value? Or sometimes we don't even know what is the value stored in the flip-flop. So we want to say, okay, I want to set the value Q to 0. I don't care what's the value right now. So what can we do? Okay, so now that's your turn. So I'm going to again post these questions on the Blackboard discussions. So you can actually discuss the problem, discuss your solution, and so then we'll go from there. Now let's take a look at another example. I want you to apply the principles of DeMorgan theorems to simplify the following circuit. Okay, now what's the steps you need to follow to do this? Now let's first forget about the DeMorgan theorem. Let's first think about what are the steps, what are the procedures of simplifying these circuits. Now take a look at some previous slides. We talk about 3 steps, right? Step number 1, we need to find out what's the logic expression for these circuit. What's the logic expression associated with this circuit diagram? And then once you got the logic expression, then we apply all these identities, okay? Logic identities we just talked about, including the DeMorgan theorem, to simplify these logic expression to reduce the number of operators, right? Now, step number 3. Then we need to draw the circuit diagram for this simplified logic expression. Okay. Now here in step 2, you can think about how to apply the principles of DeMorgan theorem. Okay, so that's basically happened in step number 2. So I'm going to post this problem again on the Blackboard. So I will put in the Blackboard discussion so we can have some, discussion. So that's pretty much all for module 3. Bye.